So let's slowly start. I hope you all enjoyed the first day of the school, and welcome to the second one. So let's by the way, one thing, do you hear me now better? So yesterday there was someone saying was too low the voice, but now you hear me better. Very good. So let's come back to where we ended yesterday. So we actually ended by saying, now assume that we have a Lagrangian, which gives us masses for charged leptons and also for neutrinos. May it be that neutrinos are Dirac or Majorana, but we get masses also for them. Then we said that's the moment where we know that we have to change from the interaction basis to the mass basis. And this we do with unitary transformations. I just remind you of the form how we said we can actually diagonalize the charged lepton mass matrix as well as the neutrino mass matrix. So remember, if I write a D, this is for Dirac neutrinos. Perfetto, grazie mille. And this is the alternative. So these are Dirac neutrinos, and in case they're Majorana, remember, since this is a mass term which connects fields of the same type, we have to use the same matrix, but this is no problem. This is indeed possible because the Majorana mass matrix is always a symmetric complex matrix. So you find the matrix you knew which actually does this diagonalization. So since you might, in one time in your life, be asked that you actually get some form of a mass matrix for charged leptons or for neutrinos, and you might be asked, actually, how do I calculate these matrices, right? In particular, how do I calculate UL and nu? Because I remember that we said that actually, when changing from the gauge basis to the mass basis, we said that we see in the charge currents, we get the PMNS matrix, which has this form. So if you want to calculate the PMNS matrix in some model that the person gives to you, where you have specified what are the mass matrices for the charged leptons and for the neutrinos, you really need to know how to calculate the UL and the nu, right? So just to say, in case ever you are asked, the easiest way to calculate these matrices is that in case of ME, you look at the combination ME, ME dagger. So this is the Hermitian matrix. Then with this information from above, you know that this should be equal to the diagonal matrix, which contains ME square, MU square, and M tau square. So this actually, just to say, if you, I suppose you're all familiar with, for example, Mathematica, you can use this immediately. If you have a mass matrix, usually it's easy if it's a 3x3 matrix, just complex, you make the combination ME, ME dagger, and from there you have suitable commands in Mathematica with which you can do this diagonalization and extract the matrix UL and also get then the mass eigenvalues, right? Sorry. I just checked that my convention, I changed my convention, and I should, for this reason, you see, because above we have UL dagger, ME, UE. So if you now imagine you do this combination, UL dagger, ME, UE, we know this should be the diagonal matrix. Now you put this combination daggered gives me UE dagger, ME dagger, UL. This gives me DE dagger, but this is a diagonal matrix with the masses are real and positive. So this is dE dagger equal to dE. And then you end up with what I wrote down here, namely this is UL dagger, ME. You would get a UE dagger, but this is 1 because it's a unitary matrix. As we said yesterday, these are the transformations which we use, and you get this UL. Okay, just to explain you, there's no magic in getting this equation, and this is the equation one usually uses if you are asked to compute this piece. Analogously, if you are asked to compute also what this transformation matrix you knew is, you do the same, and this you do independently of whether the neutrinos are Dirac particles or Majorana. So if they are Dirac particles, we just copy what we do for the charged leptons. So this would be U nu dagger m nu d dagger nu should give us m1 square, m2 square, m3 square. And you do the same. Actually, there's no difference. If you have Majorana neutrinos, you can do the same. You get the same. There's one thing in addition that you have to do. You then, first you get here for the Majorana neutrinos, you first get a solution, which is your U nu, which actually does this job. So you get a matrix. But then you have to check, in addition, if this is Majorana, that really this condition down here, no, that you have U nu dagger m nu m, U nu star actually is true, that this gives you m1, m2, and m3. So this condition, you might think that there might be huge problems in order to really fulfill this once I have this U nu, which I get here. But no, the only thing which you usually have to adjust in order to really get that this is m1, m2, m3, where we understand that since we are talking here about masses, they have to be positive, right? They have to be real numbers, they have to be positive. The minimum, as we were seeing, and we see also here at the, on the slide, is 0. So what do you have to adjust? When coming from here, already having the solution for the U nu, and you want to get the U nu, which actually also does this job, usually you have to just adjust the faces of the different columns of the matrix U nu, which you can do. This is no problem. This usually works. This is related to the fact simply that neutrinos are Majorana particles. You will definitely have a chance when going to the tutorial with Joao to discuss this more in detail and to have also numerical exercises and practice this, right? Because I think this is, I mean, it might be very easy. Or usually people think that this is very easy, but it's good to know really how to compute this for some example and to really be able to compute a PMNS matrix in real life if you ever have the need to do this, right? Good questions regarding this? Yes, of course. Would you have an idea how to do this? So now we have used this combination M dagger, right? What happens if we switch? Exactly. Just switch the combination. Instead of computing M dagger, you look at the combination M dagger M, and then you get the matrices, the corresponding matrices for the right-handed ones. Good question, thank you. More questions, comments? If not, I would say let's move on to the PMNS matrix. And so yesterday we ended up by having this as the definition of the PMNS matrix, which then appears in the charged currents. Just to remind you, the corresponding Lagrangian would be minus G over square root 2 W mass, then left neutrinos and mass basis, gamma mu, the PMNS matrix daggered, and I have the the left-handed fields for the leptons, charged leptons also in the mass basis. So here it appears, like we would expect, also similar for the Decay matrix in the quark sector. So now one thing which you often hear or see that people say is that the PMNS matrix relates the neutrinos, the flavor eigenstates, to the mass eigenstates when the charged leptons are already in their mass basis. So this is to say, if so the charged leptons are in the mass basis. So this just means the matrix ME is right away diagonal. So we don't need to do any job for the ME, right? Which would say we take our CC Lagrangian and we would write it more in this way by saying this is d divided by square root of 2 W plus, and then we would say we group actually these ones together just to make it clearer, right, that you have this form. Now, what is this? This, you would say, actually should be the left-handed neutrinos in the, now I invent a new name, in the flavor basis. So you would read off that from the new left flavor, you get to the new left mass. Let me write the M out as mass via this transformation, right? This is actually what people very often say. This is really connecting the flavor and the mass eigenstates of the neutrinos. Because they think, okay, I have the freedom to choose a basis in which the charged leptons anyway already have a diagonal mass matrix, so I only focus on the neutrino sector, which is fine. And so this is, I mean, you could say this is purely conventional, but this is usually how actually the elements of the PMNS matrix are named. Because if you look at, you have seen already yesterday in Maura's presentations, the explicit form of the M beta beta. And there certain elements of the PMNS matrix appear. So if I now have that my PMNS matrix connects flavor eigenstates and mass eigenstates for neutrinos. Usually the flavor eigenstates have an index alpha, so which is E, mu, and tau, while the mass eigenstates, they have an index I, which is 1, 2, 3, because they belong to, we call the masses 1, 2, 3, right? And correspondingly, then it makes sense to call the elements of this PMNS matrix according to which flavor they connect with which different mass eigenstate. So this is why we call the first element UE1, the second UE2, the third UE3. Then we have mu1, mu2, mu3, tau1, tau2, tau3. Just to say, this is the meaning of why people actually use this notation and give these names to them, simply because thinking in this basis, you see that there's really the connection between the flavor eigenstate and the mass eigenstate, and the components of the PMNS matrix tell you how much of each mass eigenstate is contained in a certain flavor eigenstate. So this is the point of the elements of the PMNS matrix. Yes? Good. We already said that this matrix is unitary. So one question to you. You remember how many parameters does the Decay matrix have? Or which parameters of the CKM matrix do you know? Yes? Correct. If the Wolfenstein parameterization is very suitable, it's a very good approximation. If I don't want to use an approximation, but I would like to have an exact parameterization, because the Wolfenstein parameterization plays with the fact that the lambda is my expansion parameter and I just go up to a certain order in lambda. What are the parameters which one usually uses if you want to parameterize exactly the CKM matrix? Exactly. So again, they have four parameters. No, it's just three real ones plus one phase. So in this sense, the Wolfenstein parameterization reflects all the important physics. But if we want to go for an exact parameterization, why do I insist here on an exact parameterization with no approximation? Is because we will see for the PMNS matrix, I don't know, we don't have really a small parameter, right? There's no equivalent to the Wolfenstein, or not so easy, or at least we think that this is not so clear that we have an equivalent to the Wolfenstein parameterization for the PMNS matrix, so we just base ourselves on the most general parameterization which we can use for unitary matrix, which actually now we start again with neutrinos being Dirac particles. So if neutrinos are Dirac, then UPMNS has three angles and one phase. So exactly like the CK matrix. So and we use exactly the same parameterization which you find for the CK matrix in the PDG. We use exactly the same for the PMNS. Let me just write it once for good, that we all have it in front of our eyes. So you would get C12, C13, S12, C13, S13 E minus I delta, and S12, C23 minus C12, S23, S13 E I delta. So these elements are a bit longer, more C12, C23 minus S12, S13, S13 delta, and the third one also fits in here, is S23, C13, and the third row we also do S12, S23 minus C12, C23, S13, EI delta, C12, S23 minus C12, C23, S13 delta, and then I get the C23, a C13. So now I have to explain you the S's and the C's which are used. So Sij is shorthand for sine of theta ij, and Cij is short for cosine theta ij. As you can see, we have three different combinations of these i's and j's, which means we have three different angles, and we have one phase. We have this, the delta is usually the phase, which is called in our case also explicitly called the Dirac phase. Just to insist that this is related to the Dirac nature, this is the exact equivalent of what we have among the quarks. So if we have theta 12, theta 13, and theta 23, This one is conventionally called the 1,2, the solar mixing angle. The 1,3 is the reactor mixing angle. And the 2,3 is the atmospheric mixing angle. So this is, I say historically, because these were kind of the most dominant sources of neutrinos. So solar neutrinos, which helped us to measure first time and well theta 1,2. The atmospheric mixing angle was measured first time and well with the help of atmospheric neutrinos, so neutrinos produced by cosmic rays in the atmosphere. And the theta 1,3, we had to wait for a long time until 2011, 2012 for the first measurement of theta 1,3, and this was all with the help of electron neutrinos coming from reactors. So this explains the nomenclature well. We call them with these three names, and they are still today called in this way. So now, again, we come to something practical. If you are asked once in your life, that might happen to you, then you get a PM&S matrix in front of your face and you have to extract mixing angles. So how do you do this? Usually, there are different ways. The easiest way to extract the solar mixing angle is you take the ratio of the absolute value of the UE1 and the UE2, then you would get the tangent or the cotangent of the theta 1,2. Okay? Then, since we all use this as standard parameterization, if you want to extract the atmospheric mixing angle, you take the ratio of the U mu3 to the U tau 3, which gives you the tangent. Always take the absolute values because you might have some unphysical phases in some way if you're not exactly in the parameterization, which are written down. So you take the absolute value of this ratio, which gives you the tangent. And the third one, even easier in this parameterization, the absolute value of the UE3 is giving you the reactor mixing angle, so the sign of the reactor mixing angle. Regarding the, yes, please. I mean, the particular reason is what I was saying. This first, they were observed in measurements using neutrinos from the sun, so you call them solar. Neutrinos, solar mixing angle. Theta 2,3 was the first time measured, or really is predominantly measured, or its value is driven usually still by neutrinos that come from the atmosphere, which means they are produced with cosmic rays in our atmosphere. So this is the dominant transition. And for theta 1,3, yes, this was dominantly measured by 3 reactor experiments, which are called Diabay, Reno, and Double Show. So now all of them are phased out and people do something else. So it means actually it profits from the fact that you have these delta m squares, which have a factor of 30 between each other. So if you take the ratio of here this 2,1 is called the solar mass splitting usually, and the 3,1 or the 3,2 is usually called the atmospheric mass splitting. So if you compute the ratio of these two, you find out that the atmospheric mass splitting is around 30 times bigger than the solar one. Now we are going to come to the discussion of neutrino oscillations, which tells you you have a certain hierarchy in the oscillations. And which means, depending on the source and on the distance between the source and your experiment, you have the possibility of having the dominance of one or the other oscillation, right? So, which means theta 1,2 together with the delta m21 square is easiest measured, or it was first measured in just looking at 2 flavor oscillations and analyzing data from solar neutrinos. Right? The same is true for atmospheric. And for the reactor, is more complicated. You can't do actually an approximation. You have to go through the 3 oscillation formula, right? Is that now clearer? Good. One other thing you can observe, what happens if θ13 is 0? Just looking at this parameterization. If θ13 is 0, the sign is 0, and you lose any dependence on the phase delta. Okay, this is this explains you why historically people were very much after the fact of knowing whether this θ13 is really extremely tiny or whether it's decently large, which nowadays we know it's of the size of the more or less the Caribou mixing angle. It's a bit smaller, but more generally speaking, it's not only true for θ13, it's also true if you look at the structure of the matrix, it's also true for θ12 or θ23. If any of these 3 was 0, we would not have any CP violation possibility. And indeed, if one asked you to extract the phase delta from the PM&S matrix, the easiest thing to do is that you look at a certain combination of elements of the CK matrix. For example, I give you one example. I don't want to show you the general formula, but there is a general formula as well. I give you one example. This is, for example, you can look at the imaginary part of UE1, U1 star, U2 star, U2. For simplicity, I give you one example. This actually, if you go through this, gives you the value of delta. No, not exactly the value of delta, but if you compute this, I'm not forcing you to compute this now from the top of your head, but if you explain, so write it in this, with these elements, and you find that actually this is 1/8, the sine of 2 θ12, sine of 2 θ23, sine of 2 θ13, the cosine of θ13, and the sine of delta. So this is a way how you compute, usually, if one asks you to compute sine delta from a matrix, like this, you do this, okay? So you take combination of the imaginary part of this for different elements, so you can actually generalize this. It does not have necessary to be UE1, mu1, E2, and mu2. I think Joao will also talk a bit more in general with you about this. But if you express it, it turns out to be all the viable combinations which you can take of the 4 different elements and take always the imaginary part, because we are interested in CP violation, so we need the imaginary part, always give you that this is proportional to the sines of 2 times each of the mixing angles and times the sine of delta. So what does it tell you? If JCP, when can JCP be 0? Just to say, give you an example. So if any of the 3 mixing angles is 0, so this explains you we always only have CP violation if all of the 3 mixing angles are non-zero. If any of the angles would be pi/2, we would also end up that this is going to be 0. And obviously, if delta is 0 or pi, then also JCP is 0, because then the sine delta is 0, right? So, which means whenever we see, so this explains you why delta being 0 and delta being pi usually are called like no CP violation or just trivial CP phases. And we use this JCP, which is in honor of Cecilia Jaskog. It's called the Jaskog invariant. This is also the exact equivalent which we are using in the quark sector, right? So this much about the PM&S matrix, its parametrization, and extracting the CP phase. Any questions until here? Or Is it too complicated, too easy, or is it okay? Hmm? Okay, good. Thanks for the feedback. Mhm. 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 Exactly. Exactly. S- You would not necessarily see it from this matrix because you always have to take into account that I've written down this in what is called the standard parameterization. But this standard parameterization is kind of up to unphysical phases. Some rephasing, which you can always do to your fermion fields, which still leaves the rest of the Lagrangian invariant. And for this reason, definitely it's not recommended that if you have some, let's say, numerical form of this PMNS matrix, don't try to extract the delta by just taking here the imaginary part of it. You take this because we know that this is really invariant, so it's called a CP invariant, which means it's exactly constructed in this way, such that with this imaginary part of this combination of the four elements, such that all these unphysical phases, which otherwise can blind you from really seeing whether there is physical CP violation, are taken into account and they go away. Does this answer your question, Giuseppe? So in this sense, sometimes people might get confused if you just see some complex element here. Does not necessarily mean that you really have CPU. Check whether this is not related to some rephasing which you can do with the fermion fields. And for this reason, we have our community. See? Yes. Yes, please. Mm-hmm. Exactly. So that's why if you want, so keep in mind that this is not each of these elements, or this matrix is not necessarily physical. I mean, the parameters which are contained in there are not 9 independent complex parameters. The physical parameters are 3 mixing angles plus 1 phase. Of physical quantities are also obviously transition probabilities for having oscillation between an electron neutrino, muon neutrino, and compare this to what do the antineutrinos, for example, right? So just not to get confused, sometimes this matrix seems to tell you more than it actually does, in the sense that it's always reducible to only for a maximum for independent physical parameters. The rest might be, it's just unphysical phases, okay? Good, so now, what shall we do? We said, I started by saying, if neutrinos are Dirac, then it looks exactly like this. So what happens if neutrinos are Majorana? What happens if neutrinos are Majorana? We come back to the freedom of phases and of absorbing phases and whatever. If neutrinos are Majorana, I don't have the same possibility and power to absorb unphysical phases, and some phases which were unphysical in the case of Dirac neutrinos become physical. So essentially it tells you that if neutrinos are Majorana, the matrix looks like this times a phase matrix. So let me write it down. If neutrinos are Majorana, then we have maximum 2 more CP phases. They are usually called, let's say, not usually, they are according to the PDG, it likes to call it eta 1 and eta 2, and they have a range between 0 and pi. And where do they show up? So it's like if we call this now, sorry, let me call this the PMNS for Dirac, then you would say the PMNS for Majorana now is like the PMNS for Dirac. So 3 mixing angles times eta I e to the I eta 1, e to the I eta 2, 1, and this is 0, 0, 0, 0, 0. I add the diagonal phase matrix. So why do I do this? This comes back from the fact that I have less possibilities now to absorb these unphysical phases. Where does this restricted possibility come from? It exactly comes from the fact that, remember, a PMNS matrix is computed by having the mismatch between this UL and the U nu. So PMNS is UL dagger U nu, but U nu for Majorana has the job to diagonalize alone the mass matrix for the neutrinos. So if I force you to impose this condition, this boils down to fixing the phases here, up to one overall phase. Okay, this tells you you have no more freedom to actually absorb further phases in this U nu, or to say in the corresponding neutrino fields, because you are connecting. Always remember, if you want to see it more physically, you're connecting in the mass basis. Now let's write the mass term for the neutrinos, the Majorana mass term for the neutrinos in the mass basis is nu Li bar nu Lic. So if you have your nu Li fields and you give them an additional phase, what happens? So you say the nu Li goes to E I alpha nu Li. I want to do this. What happens? Can I do that? Or do I change something on this term? They don't cancel. So if I do this transformation, which must mean if I use the bars, I get a minus in the exponent here. If I use the C, I also get a minus because it's a conjugation. This would tell me I transform to Mi E minus 2 I alpha I bar C. And I have introduced a phase in there where actually I want to read off my mass term, which should be positive, okay? So that's not possible. I would do something which I can't easily otherwise undo, okay? So I'm not allowed to do this. The only thing which I would be allowed, there's always this trick of having an overall phase you can always get rid of. But if I do this for one and I do it differently for the 3 different generations, no, this is not going to work, okay? And obviously this is different. If you imagine that you have now let me erase this, and we do this counterexample. How does the mass term for the electron looks like? The mass term for the electron is the left-handed electron bar times the right-handed electron, okay? If I do something to the faces of the left-handed electron, I still can absorb this in the right-handed electron. Just redefine the fields. No problem, I can do this. If I have a Dirac mass term, it's just saying I have more phase freedom than I do for a Majorana mass term, okay? This is This explains you why here we have these two extra phases. Is this clear or? Mm-hmm. I mean, this now, you imagine that you have used you knew in order to diagonalize this matrix, right? But still, you have the obligation that M1, M2, and M3 are really positive or zero at minimum. And usually you use then the faces of each of the columns of the UNU in order to make these things positive. Okay, this is like decomposing the diagonalization process in two steps. One step is you make it diagonal. The second step is you arrange the phases such that really M1, M2, M3 are positive or zero, which means you are in this situation where you have Mi, maybe complex, LEI bar, LEIC, and here you see you can use this phase freedom once in order to make this thing being positive or zero. But once used this, you stay in this basis, okay? Otherwise, you would add a phase here again, which you don't want. This is the reason why essentially you have this additional 2 degrees of freedom, these phases which come in. Now, clearer? If you exactly. You would just say like, okay, then I have what kind of situation? Neutrinos are Dirac. I would be in this situation. This is a totally different field, independent of it. Okay, then do something to the phase here. You get a phase, but you can absorb it by doing the corresponding phase transformation also to the right-handed field. Simply this you don't have for Majorana, because they are connecting fields of the same type. Mm-hmm. Mm-hmm. I point just to Joao. That's his job. Yeah, no. I mean, he prepared. He did already a great job and prepared a lot of exercises. So he's well prepared for all your questions that can come up, and that you have the chance to practice, which I think is necessary, because it is not clearly is not obvious if you just hear it from someone who did this thousands of times already. But once doing it yourself, then it is clearer. I think it becomes clearer then with time. Okay. So, shall we go on then with this, that you have to live with the fact that there are two more phases, right? And these phases are actually, because they depend on the nature that neutrinos are Majorana, they are called Majorana phases. So these are Majorana, just to distinguish from the fact that the Dirac is the Dirac phase, so the delta is the Dirac and the etas are the Majorana ones. That also is now the quest is then the question how to measure these, right? And this again brings us back to the main theme of this school. So that actually until today the most model independent process and most promising way to ever measure a combination of these Majorana phases seems to be through neutrinos double beta decay. And we will come to this point that this actually is not telling you exactly what eta 1 and eta 2 is, but there will only be a combination. If you remember of what you have seen from Maura yesterday of the combination of the M eta beta, I also think I have it here somewhere. Wait a second. Here. So you see this one comes up here and up here, but you have two phases, right? And then you have other stuff, and you have one quantity. It's not possible to actually determine exactly both of them, but at least the combination we can get. So this is good. We will discuss this in more detail, and also we'll have You will have some dedicated exercise also to convince yourself on how this works. Then something else I wanted to tell you. One last thing. I will just say it, and I think, Joao, you are going to show it with them together, to find it out with them, because we still don't know what the lightest neutrino mass is. Could be 0. If the lightest neutrino mass is exactly 0, you don't have 2 Majorana phases, you just have 1. That's also something to know. And you just lose one physical parameter, and it turns out to be just one additional phase. So, and maybe, I don't know, Joe, I don't think we have an exercise, but maybe you can also think about with them together, just for fun, how can you extract eta 1 and eta 2? We have, good, very good. So, because I told you at length the usual story with the Judskog invariant to extract delta. So, together with Jar, you will explore how to extract eta 1 and eta 2, just that you also know how this works. Good. Now, what I would like to do, I would like to tackle neutrino oscillations with you. So I will do the very simplest thing and present you the easiest way of ever getting a result for neutrino oscillations. First of all, we like to study neutrino oscillations for 2 flavors. So we forget about the fact that we have 3. We say, okay, start easily, just start with 2. And we do this and in vacuum, which means we are not studying here matter effects, which are highly relevant for solar neutrino physics. And so we keep our life very easy. Yes, exactly. So I just leave the more difficult task to Joao. So one first very basic thing, what do we understand about, what are neutrino oscillations? Just so now this picture makes you laugh because I'm a theorist, but my interpretation of neutrino oscillations is the following. You have 3 stages. You have a source, which produces something. It produces neutrinos or antineutrinos, but it produces, this is important, flavor eigenstates. It produces a new, always left hand, new L alpha, okay? Or a new bar, but it produces flavor. Because they are produced, they are born in some weak interaction. So if they are born in a weak interaction, they are born as flavor eigenstates. Then, at the detector, you have something, whatever, I'm a theorist again. You have something, whatever, water, liquid scintillator, ice, that is material that which the neutrinos interact and stuff. But again, how do they interact? They interact through weak interactions. So they are produced, they are also detected in terms of, again, flavor eigenstates. So this is what happens on the source and the detector. What are they doing when they propagate? So they are propagating in vacuum, which means there's no way of what they interact whatsoever. It's just vacuum. So they're just free particles happily traveling around. But they're then, so then we are talking about physical particles with a definite mass. If we talk about propagation, which means they are propagating as mass eigenstates. So there you see that actually making this transition from being produced as a flavor eigenstate to propagating as a mass eigenstate, and then being again detected as a flavor eigenstate, we involve the PMNS matrix, right? There it comes in. So far, so clear? Good. Now, we discussed the PMNS matrix for the 3 neutrinos. Now we are more modest and do everything for 2. Okay, being more modest reduces the 3 by 3 matrix to 2 by 2 matrix. So if neutrinos are Dirac, then the PMNS, let's say 2 by 2, it's just cosine theta, sine theta minus sine theta, cos theta. One physical parameter, just one angle. In particular, no CP violation. If you have Majorana, as you might imagine, story is slightly different. Your 2 by 2 PMNS looks, I mean, still just one angle, obvious. No, but also one Majorana phase. So this tells you one angle only, and this again, if you do the game of rephasing, tells you one angle and one Majorana phase. So what we are going to do in our calculation, we use the more general way, all right? You see immediately then that the form of the PMNS for the Dirac is comprised, so to say, in the one for the Majorana. So we try to make things as general as possible, so we take the Majorana. And we want to ask a simple question. 2 flavor oscillations. We ask, okay, I have a source where neutrinos are born as electron neutrinos. Somewhere I sit with a detector and I want to detect muon neutrinos. So my question is, so nu e at source, nu mu at detector. So I want to calculate mathematically, or physically, I want to calculate this transition probability. That's my question. Because I will say now, I do 2 flavors. I call the 2 flavors nu e and nu mu. These are my 2 flavors. And my 2 mass eigenstates, I call nu1, nu2. I mean, there's always an L for left-handed. I just drop it. Please forgive me about that. So, which has mass m1, and this guy has mass m2. Okay. This is the setup. This is what we want to calculate. Now, the calculation can be done in many ways, with many complications. I will just briefly mention these complications at the end. But if you say, what's the easiest theory I can use, the easiest framework I can use, then you say, okay, I use quantum mechanics. I don't use QFT. I don't use anything complicated. I just use quantum mechanics as you learn it at the level of bachelor. And then I would say, having this form of the PMNS matrix, I can write what the state nu e is in terms of nu1 of these states, nu1 and nu2. This would be the first job, right? Because if you want to say, I produced the nu e, then I have to propagate, and then I have to detect also. But how can I translate the flavor to the mass eigenstates. Exactly, this is through the PMNS matrix. And if I write it in the form of states, it actually looks like this. You might be a bit irritated, but think for a second that actually it's not going with the PMNS, it goes with the PMNS star, so which explains you the minus sign here. Maybe you can discuss with Joao if you look more deeply into that, but this is how the states are written. So now, what's the question actually, this transition? How would I write then this transition if I have this? So what do I have to do? I start now with a new E state, right? I can write it in nu1 and nu2. This is fine. Then we have to do this propagation, so they propagate with nu1 and nu2. But then I have to have like a new E at the time t when I detect this is t at the detector. So this is kind of like this guy travels a distance. This means like my new E state propagates with time. And now I want to find out how much in this guy is nu mu, so to say, right? You know how to do this in quantum mechanics. Quantum mechanics, you would say, okay, then this is nothing else than making the computation of this matrix element or this scalar product, the absolute value square, so to say. You do that. Okay, so this is what actually is like you can do with students who did the first quantum mechanics course. Now, how actually get to the new E t here? How do we get there? So we first have to agree what actually do we would like to use as time evolution for the states. Again, we make the simplest thing possible. So again, the very simplest thing possible, if you have no idea of how a particle propagates, the easiest thing what you can do, what it is. What is this? Plane waves, exactly. No idea. I use a plane wave. Obviously, it's not describing a localized particle. No, I mean, plane waves is everywhere, but I have no idea of how to describe it correctly. I use a plane wave. Okay. Do plane wave and see whether it gives a meaningful answer. So that's the point. So we start with a basic thing is for the propagation, we assume propagation as plane waves. So this is obviously highly doubtful because, I mean, this is a particle. I mean, particle has a certain localization. I mean, it's a wave pattern, more likely. It's not a plane wave, but okay. We have no better idea. We do the simplest thing possible. If it's a plane wave, we know how to propagate the nu1 and the nu2. How do they propagate? Plane wave. And let's put the h bar because we are in quantum mechanics. We are not yet in QFT. Exactly. So what are these E1 and E2? What are they? What are they? See, whoever knows what they are, please raise his, her voice. What are they? How can I describe E1 and E2? On what do they depend? These are just the energies of the particles, okay? So perfect. So usually you would write this as being something. Now let me see. I have to recover all the factors of C. Usually I never use this, but okay. Let's recover all factors of C. It's this, okay? Just relativistic. where the mi is the mass and the pi, the tray momentum of each of them, which we also have to define later on, right? So this is, we have to understand what to put here and here, okay? So, but now we have all ingredients and we do the calculation. We are ready. Good. So we compute the first oscillation probability. So so we do write the nu mu as the in terms of the mass eigenstates, taking into account the conjugation because we have a bra instead of a cat. I get this, and I have to write down the nu e evolved with time. So I use this time evolution, right? I'll just throw it in. It's going to be the cosine e minus t. I have minus e I1 t divided by h bar, nu 1. That's a plus sign. I have that's a sign. E minus 2t divided by h bar, nu 2. This. So usually what we always assume that if we have like some basis, and these are the bases of the two states, then you know our states, usually in quantum mechanics, you always say I have states which are orthonormal, which means scalar product nu 1 with nu 1, or nu I with nu I is 1, and nu 1 with nu 2 is the same as nu 2 with nu 1. That's 0. Okay, this is the condition of orthonormality, which you have always if you consider a basis. Usually you choose it in such a way, okay? This is okay. We use this in order to simplify the result above. So, what happens if we multiply out this parenthesis inside the absolute value square, making use of this? So, we will get a combination of this first term here with the first term here, right? Get this one. So you please check that I don't make any typos. So this is minus sine theta minus cos theta. I will get the e I eta. I will get the e minus I eta. I get the minus I e1 bar. And then I get the scalar product of 1 with 1, which gives me 0. I neglect all the cross terms which combine 1 and 2. I focus just on the 2 with the 2, which gives me cosine theta sine theta minus ei2 t and bar. Again, there's the scalar product 2 with 2, which gives me 1. Okay. What do you observe? Very good. The Majorana phase goes away. This happens always for neutrino oscillations. Also in the case of 3 flavors, you are not measuring Majorana phases in neutrino oscillations. You are not sensitive. So now this is the, let's say, calculational result. What is the physical reason for that? Why? Can you understand this? Are you awfully surprised by this? This is the shock of your life, and you probably would like to give up on physics and just lost all your hope and whatever, and I don't know. So it's like exactly, so what the hell? What's the physical explanation? But if you think in terms of lepton number, so we learned that if you put a Majorana phase, or if you put a Majorana particle, it violates lepton number. Would this process violate lepton number? Does a neutrino oscillation, can it violate lepton number? When could neutrino oscillation violate lepton number? I mean, be a bit more exotic, not that conventional, okay? If I look at the neutrino oscillation, nu to nu bar, okay? I change from nu, which has lepton number +1, to nu bar, which has lepton number -1. I would do a transition of delta L equals to 2, and this would be, I mean, would be a lepton number violation. What I do here, from a neutrino to a neutrino, doesn't matter. I mean, I have to be blind with respect to any lepton number violation, because this process works without lepton number violation. I don't have any insertion of, I mean, it's clear I don't have any sensitivity to it. In contrast to neutrinos double beta decays we have seen yesterday with Majorana, if lepton number is violated, then I have a chance to be sensitive. If I don't, necessarily, everything which is sensitive, I mean, makes a difference between Dirac and Majorana has to drop out. And this is what happens for the Majorana phase here. So it's like it's going to be irrelevant, just irrelevant. I mean, this is neutrino to neutrino. I mean, not to say that, I mean, in the beginning where people didn't really know what, I mean, even before having detected neutrino oscillations, people were thinking in all different ways, right? You have, for example, among mesons, you have KK bar mixing, right? You can go from a kaon to an antikaon. Why not going from a neutrino to an antineutrino? Or why not going from a neutron to an antineutron? The question is always, you could in principle, right? And you have these type of processes, then you would violate a certain quantum number, a certain symmetry, whatever. I mean, here we are not doing that, right? We are not doing that exotic things. You could do these exotic things, but here we are just doing conventional neutrino to neutrino, no lepton number violation. No sensitivity to nature of Majorana. Yeah? Does this make sense? So we are almost there. You can write this a bit nicer. So, okay, you get the sine square of theta, cosine square of theta. You also can write it as 1 minus E minus E1 minus E2 t divided by h bar. This. And then you can remember what kind of what kind of rules you have for trigonometric functions. You massage this. You remember the relation between the exponentials and sine and cosine. And you would say, I actually can write this in a nicer way. For example, what can I do to the first term? I can write this as a sine square of 2 theta, but then I get 1/4. And this one, in principle, could also already rewrite. But let's first analyze it a bit better, because that's probably easier. So what is, one question to you, what is disturbing about this? Why is this really not such a useful formula? I mean, most of you are experimentalists, so you should probably realize more easily than me why this is nothing that you want to, I mean, one thing, yes. Another thing, how actually would you measure the time? I mean, I don't know. I mean, do you have any idea? You give to every neutrino, you give a small Apple Watch, you say, take it with you, then just stop the time and we see what happens and go ahead. No, I mean, usually the most difficult thing you would see is like how to measure this time. But I mean, we can do a very crude approximation, right? We can say, what do we have as information? We have as information, neutrinos are very light. So, which means they move practically at c, so speed of light. I mean, they have mass less than an electron volt, they move practically at the speed of light. So we know the time, so we know, and we can be really very rough. We say like, okay, if I can't measure time, at least I can measure a distance. So I can measure, I mean, usually I have a good idea where my detector is and where the source is. So I take a meter and I measure. That might be more, usually kilometers or hundreds of kilometers, but that's something I can measure, okay? This is the distance between source and detector. This is a very crude approximation, okay? This is definitely not the final answer, but this is the easiest thing you can do. And this, I mean, you just test whether this works. Put it this way. We are usually physicists. We always say, okay, make our life easier. We do some approximation. We know that there might be some issues with this approximation, but we go ahead as long as we are not ruining fundamental laws of nature. And we just try to go ahead with the easiest formulation which we can find. And later we can always improve, hopefully. So, which means here we will put minus I, E1 minus E2, L, sorry, this one, L over H bar C, absolute value square. I mean, outside this one here. So, and then now we come to the point which you had, which was actually we're having this difference of energies in there. And now we are not going to use this exact formula, okay? We are actually saying, to compute this, we first start with a EI itself. So, okay, exactly, it's going to be the square root of MI square C4 plus PI square C square. So, I can do a Taylor series. So I for sure know, or in all physical purposes for neutrino oscillations, I know that the mass is much, much tinier than the momentum, than the energy. I mean, now this is written, sorry, forgive me, this is written in naturally, I mean, I don't want to restore. Please restore appropriate factors of C, but I just want to make clear that we do a Taylor expansion. Okay, we do a Taylor expansion in the mass divided by the momentum, and this we do up to the order which we need. And let me do one thing. I really would like to set C equals to 1 in this moment because I really don't want to restore this. I know this makes usually experimental physicists are getting unhappy, but theoreticians I get very happy if we don't need to drag with these C factors. Sorry, I really don't want to keep them, but I can do this. So this is an improvement because it makes the formula simpler. Now we think about one thing. So in the most general situation, you would say that every mass eigenstate has its own momentum. Let's say this momentum, however, should be related somehow to the neutrino which you produced at your source, right? And if you, again, you make the crude, I mean, you make the simplest approximation which you can do, this would be that, okay, these guys all have the same momentum. Okay, so this is the equal momentum for everyone. And in addition, you take into account that actually these things are ultra-relativistic. So in principle, I can also say that my energy is really dominated just by PIC, or just is P, okay? Just forget about the factor of C, which means this is nearly the same for everyone. So this I would like to use in this right-hand side. So I arrive at something which is, this is going to be like an, if this is just P, then I call the equivalent energy just E. So no index I anymore. So this is an approximation. This is an average value of the energy. And this is giving me this 1 plus mi squared divided by 2e squared. Sorry. So this is the simplest way in which I can approximate these energies. So by saying, what's essentially the difference between, so just by saying, what do you think? What's the most important point for me? The difference of the different energies. The most important point is the difference, is the mass. So is the difference in the mass in this approximation. Obviously, you can discuss what is the quality of these approximations and so forth. So this is definitely legitimate to do. Now, if I have to deal actually with this difference, E1 minus E2. So what do I get? This is a common factor, it drops. Then I get mi1 square minus mi2 square divided by 2e square. So this is the origin of why people say what you measure in neutrino oscillations are the delta m squares. You always measure mass square differences. The origin goes back to this difference in energy. So that's dominated in this approximation by the difference in the mass square. So usually one would say this is minus delta m2 1 square divided by 2e. So now this you all plug in. This is the moment where you plug this in here. And you use that this actually you can write as a sine function as well. May I erase this part already? Can I erase this down here? Okay, thank you. Then let me erase this. And then we complete this formula and end up that this is going to be the sine square of something, which is here. And this is delta m to 1 square from above L divided by, we get a factor of 2 there, we get another factor of 2 from the sine. Using this sign gives me 4 h bar c e. Again, I keep just for fun this h bar c, but I personally don't like it there. I usually would prefer to have h bar and c1, but let's keep it. This is the formula for the transition. So this is the simplest approximation, the simplest thing you can go through. You still get something meaningful, okay? You see here a lot of characteristics already. You see the characteristics of that this goes with the delta m square. This is what people then really measure. Since it goes with the delta m square, what do you learn? So let's analyze this. So what does this tell me? Anyone, any idea? So what happens if the masses are 0? No oscillation. What happens if the masses are exactly equal? No oscillation. So very good. We already learned something, that this tells you that this is really important. I mean, this was for them fantastic to know that there are neutrinos which have different masses. I mean, first, they have mass, fantastic. Second, they have different masses, huh? Fantastic. What is about this angle here? This is the mixing angle. What do we learn about the mixing angle? Exactly. So, no oscillation if there's no mixing. What do we learn about, what's the maximal value? Huh? No. At 90 degrees, then it's 0 again. But this is not the maximal. Well, how can I maximize the probability in order to have a transition? 45, pi over 4. So that's why people, you hear them talking all about. So maximizing P E requires theta being pi over 4. This is called also maximal mixing. So this is actually, if you think back to the 3 mixing angles which we have, I will show you in a second, this is possible for the atmospheric mixing angle still. So in all the time you read some paper that deals with neutrino oscillations, and in particular with predicting or have a theory for giving you certain values of the mixing angles, they're always very keen in getting pi over 4 because that's maximum mixing. Good. Then, what else can you observe here regarding the distance? So, if the distance is 0, do you have oscillation? Okay, so which means there's no zero distance effect. So that's what called, so you have to propagate in order to have oscillation. So this is not like, it's not a good idea that you have a small source, which is also your detector. It's not like neutrons orbit. Okay, you have to make a sort of distance. Huh? No, just to understand the features, right? So it's a very simple formula, but you can understand a lot of features already. So questions to you, ladies and gentlemen. So we are not going to do it because you want to have a coffee break as well. But if you want to compute this, what do we get? Without making any computation, you tell me what do. Okay. I get 1 minus. Sorry, I actually should have done this. Sorry, do this first. I get this because I'm not losing any I mean, if I'm in the picture of standard oscillations and I have 2 flavors, either I get an electron neutrino or I get a muon neutrino. So now, this is the non-trivial part, is if you compute this oscillation probability, you actually get the same as E to mu if you do it for 2 flavors, which means you also get the same for P nu. I'm not going to show this explicitly, but because now you should have the tools in your hands to do this yourself if you want to check it yourself and convince yourself of doing that. That's another question which we are, exactly, that's another question which we come to. If this is equal, exactly, you're right, this tells me there's T invariance. So time reversal invariance. What else does this tell me? We're not yet finished with this. What else does this tell me in that sense? Huh? So, I mean, we have always CPT invariance, okay? We are not going to destroy CPT. What actually would tell you in general CPT invariance? If I have a new alpha going to a new beta, what should be the equivalent if I do CPT? What is the equivalent of So first I have a beta going to an alpha because I revert the time. And I have a bar, I have to look at antineutrinos, okay? This is the CPT invariance. So if I have CPT invariance always, ever, and I know already that I have T invariance, what do I also have for two flavors? I have CP invariance. It just tells you that there's no CP violation which I can ever measure if I just look at two neutrino oscillations. That's good. I have to have three neutrinos. If I do only two, I will never be able to go to convince myself whether there's CP violation. If I want to write this generally, CP would say, usually people would compare CP by saying, I compare transition probabilities of neutrinos and antineutrinos. Okay, that's what I usually do. And then for T, you would say, I compare nu alpha to nu beta with going nu beta to nu alpha. It's the usual thing. And what we learned together is that for two neutrinos, no CP violation. So which means we go on with three. Can I have 5 to 10 more minutes? Would you be extremely unhappy? No, you are happy. Okay, this is good. No. I mean, no compromise on coffee breaks. No. I mean. I actually want to, we are not going to do the derivation for three, no, don't be afraid. I mean, I don't want to, because then we have coffee break, I don't know. I don't, okay, we don't do that. So maybe later. Then we do just to have like the formula at the blackboard for free flavor oscillation. So what is if I do three flavor oscillations? Three flavor oscillations, then you would say looks terrible, but actually it's derived exactly in the same manner as what we did for two flavors. It's just with three. It's going to be a little longer, but there's some real part of u alpha I star, u beta I, alpha j, beta j star. This real part is multiplied by sine square delta mij square L divided by 4e. So now all h bar and c is going to be 1, okay, really, because I don't like these ones. Then I have an imaginary part, which is u alpha star beta I j, beta j star, and then, oops, apologies, sine square, and then I get something similar. It's not exactly the same. I get delta mij square L, but divided by 2e. So the delta mij is going to be this thing, I square minus j square, which you know. The L is the distance, the E is the energy. And the U alpha I and this stuff, these are all the elements of the 3x3 PM&S matrix, okay? So, now, we make some observations. So we have not talked about this for two flavors, but if you want to apply your oscillation formulas for not neutrinos, but antineutrinos, the only difference is that instead of using the PM&S matrix, you use the PM&S matrix star. Okay, so this would mean we just now do, because why I'm talking about this stuff, because we were saying if I want to test the CP invariant, I have to look for this thing. Compare oscillations of neutrinos and antineutrinos. So if you study the nu bar, you send the u to u star. That's the simple story. Okay, so do that, you get the formula changes a bit or it doesn't change. So now, are you able to tell me what is going to change in this formula if I change the u to u star? What does happen? But does this delta change? Does this part here with the real stuff, does this change or not? Does it change? I mean, think about how the real part is defined of a number. If you have a real part of a complex number, or you take the real part of its complex conjugate, there's no change, right? What happens if I do this with the imaginary part? It changes sign, okay. So now what we learned, this is extremely fundamental. These objects here, these terms in the first line are called the CP even terms. And this one is the CP odd. Or these are the CP odd terms. So these ones. Another thing which you can learn, which might appear, I don't know, it's simple, but what happens if I actually, so I was saying, if we wanna study CP violation, we should study transition of a neutrino and compare with transition of antineutrino, because that's CP. Whether this is equal or not. And so, what happens actually if I study P nu alpha to P nu alpha? What happens to this term? So let's write this out. So it's going to be the imaginary part of u alpha I star, u alpha, u alpha, u alpha. No, so there seems to be, sorry, this should be, I'm very, very sorry, I did a mistake. This is, apologies, this is a J. Huh? Sorry. There we got J's, 2 J's. Star. Does this expression have a non-vanishing imaginary part? I mean, I can write this as the absolute value square alpha and the absolute value of alpha j. What's the imaginary part of that? Is 0. It's always 0. So it's telling you, don't look at transition probabilities alpha alpha. Look at alpha beta, okay? You have to have different flavors. Otherwise, I'm sorry, you are not going to observe CP violation. Let me do 2 little things before closing for today. One little thing is that I would like actually come back to these pieces which appear here in the signs. And I actually would like to come back to the one which we have seen for 2 flavors. This is like to help you when doing computations, okay? For the 2 flavors, you have seen that you will get a sign which depends on, sorry, a sign square which depends on delta m2 1 square L for H bar C E. So not in order to get confused and always get the numbers wrong or anything, there's a funny little trick which you can employ in order to easily compute what this argument looks like. So first go to natural units, and then if you take to be measured the delta m to 1 square in electron volt square, which is very opportune because they are they are the right unit is electron volt square. The distance you measure in kilometers, and is often we are dealing with energies which are in GeV. You find out that this funny thing, you have the delta M21, where L divided by 4E is going to be 1.27 times the delta M21 square, measured in electron volt square, the L measured in kilometers divided by the E measured in GeV. Just that, otherwise if you, just that kind of diminishes the probability that you are getting errors just due to confusion of units. So usually very helpful. Joao will have also an example with you doing that. One comment which I would like to make, sorry Joao, remind me, you also have, you're discussing this as well, right? So I just say extremely briefly, you are going to be convinced that this is always going to be JCP, either plus minus 1, okay? So either positive JCP, but this is always JCP, okay? You will see this yourself. Then we do actually, because otherwise life would be very boring, we do look at, here you have some funny picture for two of oscillation. Here, this is something you may like. I just found out myself. If you type in neutrino oscillations in Google, and you immediately come up with the Wolfram demonstration. So if you have installed Mathematica, they have a very nice public code where you can have fun with the 3-flavor oscillations. And what you see actually here would be, this is something saying, okay, it's a 1 GeV neutrino, distance is measured in kilometers. You plug in some numbers which actually are compatible with the latest oscillation data. You start with an electron neutrino. So this starts with 1, and then you see the evolution, and you see the evolution also of the muon and the tau. And what you notice strikingly, what I was saying repeatedly, because we have the hierarchy in the delta M squares, you see that there's a slow oscillation, like an envelope, and then there's the fast oscillation. This is simply due to the separation which we have in the delta M square. So one is oscillating fast and the other one is. Which is very great because that allows to use approximate formulas, also like 2 flavors, which really make your life easier instead of always considering 3 flavors. Now, if you want to know the latest data, go to the new fit collaboration, or there are other collaborations, but I just like to go to their page. They have a public web page. The latest global analysis came out 1.5 months ago. And you can have a look at the data today. If you didn't know, we were saying that delta M squares are what they are, so we've seen them already yesterday. So the sine square so usually one gives the values in sine squares. So sine square of the solar mixing angle is something like 0.3 or a third, just roughly having an idea. The sine square of the atmospheric is the largest, by far the largest which we measure. You see the 0.5 here. This would correspond to maximal mixing. So then it would be 45 degrees, really. You see this funny W shape thing, which tells you we still don't know whether this is below 45 degrees or is above. It's always going to jump around, and and actually for me as a theorist, also working in some models which try to describe and understand what these values are like in terms of a bigger theory. I actually would also know how far away, if it's not exactly maximum, most likely it's not exactly maximum, but how far away it is from maximum. Because that might be a special point for some symmetry or something like that. Here you see this one is small. So this is the sine square of theta 1, 3. this is 0.02, so which means you take the square root. So just to get the idea, the θ13 is like 0.15. The Cabot angle in the quark sector is like 0.20. We are close there. So this is our smallest angle. This is by far the biggest one in the quark sector. So bad luck for them. Good for us. Here you see what's the current prediction from neutrino oscillation for the CP phase. So you see these things go very much up and down. This is simply due to the fact that until now we don't have a really dedicated experiment. So T2K and NOVA, they give us hints. Unfortunately, they are not completely compatible with that data and predictions, but for this reason, you see these things going up and down. We are waiting eagerly for Dune and Hyper-K, that they will be the experiments which really help us to hopefully nail it down and find out what it is, and hopefully it's big. And here you see, actually, this is the JCP you've seen. This is the part which is everything apart from the sign delta, right? And you see this magnitude. This can be a magnitude, it seems to be like 0.03. So someone knows out of the top of the head, you're not obliged to know this, but out of the top of the head, what's JCP for the quarks? Any guess? If you have no knowledge and you have not yet checked the PDG on the smartphone, do you have a guess? Any guess? JCP for the quarks is something like 3 × 10⁻⁵. So we are laughing. We have the chance of being 2 orders of magnitude bigger. Obviously, this depends on the value of the sign delta. This is if it's maximal. If we have really maximal CP evaluation, our JCP is about 2 orders of magnitude bigger than the one for quarks. Bad luck for them. Nice for us. We can really have stronger signals of CP evaluation. That's good. And that's good also for Dune and Hyper-K, obviously, because it's big. We will see it more easily. And we can nail down the value much better. So now a mea culpa for the derivation was the easiest possible. We didn't do wave packets. We didn't do decoherence effects. We didn't look at QFT. We didn't take account any experimental facts and aspects related to the source, to the detector, to whatever, because also I'm a theorist. We didn't take into account any possible new physics effects, crazy things, CPT violation, non-standard interactions, whatever, which can also show up in neutrinos. Don't seem to be. All neutrino oscillation, I mean, apart from stuff. You might have heard of some kind of anomalies related to LSND, okay, before you were born, LSND, but mini boon and stuff, and micro boon, and no, I mean, stereoneutrinos, I don't like them. But okay, personal opinion. The vast majority of neutrino oscillations are extremely well described by what we have discussed today. Obviously, it's important to take into account wave packets, decoherence effects, QFT, whatever. Bottom line is these formulas are working very well, albeit all these approximations we did. What we have seen, actually, if you have neutrino oscillations, alpha to beta, just to emphasize, if neutrinos can change flavor, we know that the individual lepton numbers are broken. There's no LE, no L mu, and no L tau, but total lepton number, we can't find out whether this is broken or not with neutrino oscillations or anti-neutrino oscillations. I leave you with 2 questions. So question number 1, which just that you have fun, which you can also find on the internet, the answer. So we talked about neutrino oscillations. Why does no one talk about the oscillations of charged leptons? Why there's no oscillation between electron and muon? Not being observed, ever. And something, if you want, I will give you a reference where this is discussed, because that is funny, but would take long to include this. And another possible way of observing the violation of individual lepton number among charged leptons would be, for example, this process. I will come to this briefly tomorrow. But also this, because now the real question which I ask myself as a theorist is, or you also should ask yourself, whatever you do, you should ask yourself, because you start with a standard model where neutrinos, left-handed ones, sit in the same doublet as the charged leptons. We know that neutrinos break the individual lepton number because we have a neutrino oscillation confirmed from an electron to a muon and in many experiments and many variations. The obvious question you have to ask is, charged leptons don't do the same? Yes or no? And if they don't do the same, why not? That's the last words for today from my side. And thank you very much for your attendance.